Alright, today we are going to study Brownian motion, or also known as Wiener process. So far we have studied either discrete state space and discrete time that involves random walk or what was it? Branching process. Or we have dealt with discrete state space and continuous time, such as Poisson, or birth, death process, or reliability, or renewal, and what else? Perhaps Q also. And Brownian motion is different from all these, and it has continuous state space. So Brownian motion is here, and also continuous time. And I don't think continuous state space and discrete time makes sense, because if time step is discrete, then state space cannot move continuously. So I think this category does not exist in any sensible way. Anyway, dealing with continuous state space requires a whole new kind of calculus, which is called stochastic calculus. This is equivalent of ordinary calculus, like differentiation and integration, but instead of continuous functions or smooth functions, we deal with uh, random functions, some kind of random motions, which is not straightforward. Stochastic calculus. Of course, this stochastic calculus is not so easy. I mean, it's quite difficult, so it's actually beyond the scope of this lecture. So we only deal with it in a very informal way. So bear with that. Okay, let's study Brownian motion. The Brownian motion as a natural phenomena was first discovered by the botanist Robert Brown, as shown here. This is a Wikipedia page for Robert Brown, and he was observing a pollen grain of some plant under a microscope, and he found some zigzag motion, which he first considered to be the source of liveliness. Okay, but later he actually confirmed the same motion with inorganic material, so this hypothesis was rejected. But anyway, he discovered this phenomena, and in early 20th century, Albert Einstein made a consistent theory that explains Brownian motion, which was zigzag motion caused by collision with water molecules, and thereby conforming the notion of atoms. By this theory, Einstein was able to calculate the Avogadro's number, so which gave the support for atomic hypothesis. Anyway, let's go on and define Brownian motion. Let x of t be a continuous random variable that depends on time t. So continuous random variable dependent on time t. So consider this as something like a random variable that follows, for example, a normal distribution, which is a continuous distribution, but this distribution may depend on time t. And consider some set of time points like t0, t1, t2, up to tn plus 1. for some n, and define a new random variable d of ti plus 1 by the difference between the random variable x at time ti plus 1 and ti. Now we assume the following. First of all, these d's are independent if the time intervals are not overlapping. So independent. And also we assume that they are identically distributed. So at different time points they follow the same distribution, except that this distribution may be parameterized by the duration of this interval, the length of that interval. Except the dependence on ti minus ti plus 1 minus ti. And so this is a stationary property. So we call it stationary because at different time points they follow the same distribution. And also, for simplicity, we assume that the expectation value of the random variable x of t is 0. So on average, this random process goes nowhere. And also, we assume the starting point, the initial condition, is 0. So at time t is equal to 0, this coordinate x is 0. So this means from this definition of random variable d, we can write x of t as d0 t. And due to the stationary property, okay, due to this property, we also have x of s as d t plus s for all t real numbers. So this means this t can be any value. So because of the stationary property, we can express x of t x at any time point as this difference for any t. At this point, we define a new terminology called Levy process. So this is a stationary independent increment. So it's a stochastic process which is stationary and independent increment. So just like this, we have just defined. So this process is a Levy process. And Wiener process is defined next. The Wiener process is also known as the Brownian motion, and it is a special case of the Levy process. So Brownian motion is a Levy process with the following properties. So two properties: the initial condition, that is 0, and this d, which is of course defined as the difference between this process at different points. This follows the normal distribution with mean 0 and variance sigma squared times ti plus 1 minus ti. Okay, as we have explained before, this d, independent increment, follows the same distribution, except that it may depend on this length of the interval. And by the way, this sigma is a constant, any constant. And especially when sigma is 1, then we call it standard, the standard Brownian motion. Just like we call standard normal distribution for the normal distribution with variance 1 and mean 0. So by definition, the standard normal distribution, standard Brownian motion, if this x of t is a standard Brownian motion, then this follows normal distribution with zero mean and variance of t, right? So this is just t, since we are starting from 0. So the density function of this x, which is parameterized by time t, is this the density function for the normal distribution. Not t, x squared over 2t. So the variance is t. Next, we would like to derive the Brownian motion from as a limiting case of the random walk. So consider a symmetric random walk, unrestricted. Okay. But in this case, we make a few modifications. For example, first, time step. This is not just integers like 0, 1, 2, and so on, but it is measured in some small unit time. We call it epsilon. So t can be 0, epsilon, 2 epsilon, so multiples of integer multiples of epsilon, okay, and so on. And also the moves, let's say qi is the random walk. So increment of random walk. So each step qi could be either not just a positive one or negative one. Instead of that, we make it square root of epsilon and negative square root of epsilon. So it's a symmetric random walk. So the probability is 1/2 and 1/2. Okay. Maybe we could have written like this: probability that qi is square root of epsilon is 1/2, and same for negative square root of epsilon is 1/2. It's the same thing. Okay, so in the original formulation of the random walk, this epsilon was just 1. Okay, so just so the time step was 1, 2, 3, and so on, and qi increment was plus minus 1. But here we use a small positive number epsilon, and later we take the limit that epsilon is 0, approaches 0. Okay, then the random walk itself can be expressed as xi x0 plus sum of qi's. It's not i's. It should be something else. Let's call it j up to I. Okay, and for simplicity, we set x0 equals to 0. So this will be ignored. Now the expectation value of qi, each qi is 0. right? So 1/2 square root of epsilon and minus 1/2 square root of epsilon, that is 0. And the variance, if you calculate according to the definition, it should be epsilon. And so also, of course, we are assuming that each qi for different i's is independent of other qi's. So the expectation value of xi as defined as this summation is just the sum. So that will be I times expectation value of q's. qi. But that's 0. And this is not a good notation, but anyway, variance of xi is just I times this. Maybe I should use n here. So this is just this stems from the independence of each qi. Next, for convenience, we define x of, let's say, x of t1 as xi1, where t1 is i1 times epsilon. Remember, the time is measured in the unit of epsilon. So we can define the increment as this: t1, t2, that is x of t2 minus x of t1. So in this case, it would be the sum of j from i1 plus 1 up to i2 of qj. Okay, so the expectation value of this difference is expectation value of the sum of these j's. I1 plus 1, I2. But that is just sum of the expectation, which are all 0. And the variance of this difference will be the sum of variances of qj's, right? J varies from I1 plus 1 to I2, which is, so that will be I2 minus I1, because there are this many terms in this summation, and each variance is epsilon. So this will be t2 minus t1, because epsilon times I2 is t2 and epsilon times I1 is t1. Okay, so that means the variance is proportional to the difference in time points. Now we take the limit and goes to infinity and epsilon goes to 0. At the same time, we keep t, which is the multiple of n times epsilon. Then this random variable approaches normal distribution with 0 mean and variance of t by the central limit theorem. So now you see that the Brownian motion, standard Brownian motion, can be considered as a limiting case of the symmetric random walk. In this formulation of the Brownian motion, we needed to set the unit of time like this, epsilon. If we set epsilon, then we needed to set the step in space as square root of that epsilon. Okay, so this time step and spatial step, they are not independent, so they depend on each other. And let us formalize this concept more carefully, formally. First of all, let's say x of, so forget about this, and x of t is a Brownian motion with no drift, so this follows the normal distribution with zero mean and sigma squared t as the variance. Okay, and sigma squared is a constant. Then, if we define a new random variable w of t by x of t divided by sigma, so this sigma is the same sigma as this. Okay, then this w of t follows the standard normal distribution with mean 0, of course, and variance t. So this is the standard Brownian motion. Okay, this is an example of the scaling. Okay, so if we scale, we get the standard Brownian motion. And so let's try to generalize this. So we consider this transformation of random variable, Brownian motion. So we multiply a and divide time by b. Okay, we assume that a is non-zero and b is positive. Okay, and it can be shown, and you should try to show, that this Brownian motion, this S, is again a Brownian motion. So this follows the normal distribution with mean 0, and variance becomes a squared, sigma squared, and sigma squared is the comes from the variance of this x. Okay, and times t and divided by b. So if we scale like this, scale the normal Brownian motion like this using two constants, then the resulting random variable is again a Brownian motion but with a different variance. Okay, then if we set a equals to square root of c and b equals to c for some constant, positive constant c, then so if you substitute this a into here and this b into here, then they will cancel, and so a squared sigma squared t over b becomes just sigma squared. So this a squared and b squared will be cancelled. We have sigma squared t. So that means we recover the original Brownian motion. So if this is the case, then we have s of t is the same as x of t. And this was concluded from this distribution, but from the original definition of s of t, if you put this a and this b, we have square root of c times x of t over c. So, this is clearly different from x. I mean, it appears different from x. So this means if we scale time and space appropriately, then we cannot differentiate between the two Brownian motions. So this is called the scaling property of the Brownian motion. This scaling property can be understood in this way. For simplicity, let's say c is equal to 4. Okay, so dividing time by 4 means that we are now looking at, let's see, if we have some Brownian motion like this, so this is time. And first, let's say we are measuring this process in the unit of hours. Okay, so each unit is 1 hour. Then if we divide that by 4, then we are now looking at 15 minutes. Okay, then if we also expand the spatial dimension by square root of 4, so that is twice. So if we magnify, if we look at 4 times smaller region of time, but magnify the spatial dimension by 2 times, then this Brownian motion still looks the same as the original Brownian motion. Well, it's hard to draw such a graph, but that's what it means. Okay, statistical property doesn't change if we scale time by shrinking 4 times and magnifying spatial dimension by 2 times. Everything cannot looks the same, and they cannot be distinguished from one another. We informally show that the Brownian motion is nowhere differentiable. For that, let's see. Let's say Wt is a standard Wiener process, standard Brownian motion. Okay, and let's define its increment. So standard Brownian motion's increment is this. Okay, and of course this follows the normal distribution with zero mean and variance of delta. Okay, and this means if we square this, t plus delta squared and divide by this delta variance, then this follows chi-square distribution with 1 degree of freedom. And so mean is 1 and variance is 2. It follows that so we try to calculate the derivative of this w. Okay, so what we are going to do is calculate this quantity divided by delta. Okay, and this is of course ds of t plus delta. Now, since this d squared follows a chi-square distribution, so ds should be of the order of square root of delta. So big O square root of delta. So this quantity of this size. Okay, then we divide by delta. So the result is big O 1 over square root of delta. But this will diverge as delta approaches 0. So this means we cannot define the derivative of w anywhere. So therefore, the Brownian motion is nowhere differentiable. But still, it is continuous. Okay, it is continuous in the sense that almost surely continuous. Okay, the probability that this is continuous is 1. But still, it's not differentiable anywhere. So this is a very strange property of the Brownian motion. That's why we cannot apply standard calculus. Next, we would like to consider the problem of first visit times. So again, let's say this is x of t is a Brownian motion with this and sigma squared t as the variance. Okay, here's the problem. If we start from the origin, so the horizontal axis is time, and if we start this Brownian motion, what is the time this path Brownian motion reaches this value a for the first time? So we want to calculate the expectation value of this time. Let's call it TA. Okay. Sometimes it goes like this. It may take a long time to reach this A. Sometimes it goes straight up to A. So the time may be very short. So how do we formulate this problem? So first we define two events. Okay, A is defined to be this event. So this first passage time TA is less than or equal to some given time t. And another event B is defined to be x of t is greater than a. So this means the Brownian motion already passed this point a. Now, based on these events, we want to calculate the probability of the event A, which is actually the cumulative distribution function for this passage time, this first passage time. And we use the partition theorem, so this can be split into two parts. So A and B, or A and not B. So this is a complement of B. Okay. So these two sets are mutually inclusive, and if we take the union of these, it becomes A. So this is how we apply the partition theorem in a different way, as usual. So if we use the definition of conditional probabilities, we have probability of A given B times probability of B, and plus probability of, in this case we use a little bit different way. So instead of A given B complement, we calculate B complement given A times probability of A. Okay, first consider this probability. So what is B complement? By definition of B here, B complement should be x of t less than A. Actually, strictly speaking, it should include equal sign, but actually since this random variable x of t follows normal distribution, so probability that x of t exactly equal to a is 0, so we can safely ignore this equal sign and we can only consider less than, strictly less than a. Okay, so this probability given a, so given a means at this point of time t, the first passage has already occurred. Okay, so this means suppose let's say we have a here, so we already reached this point at least once. Okay, so x of t greater than a, it's something like this, and this probability is actually the same as this probability, same probability. No, because of the symmetry of this random walk or Brownian motion, the probability after this point, the probability that x of t is greater than in this region greater than A is equal to the probability of this part, because it's the random walk is symmetric. So after this point, so the area of this is the same as area of this. So that means probability of B complement given A should be equal to the probability of B given A. But B and B complement together, they form the universe, right? So there are no other possibilities. The random walk, the Brownian motion is either above this point or below this point, and there's nothing else. And of course, we can safely ignore that the Brownian motion is exactly at A. So that means this probability should be equal to 1/2. And next, consider this probability, A given B. Okay, probability of A given B. So this means, actually this should be equal to 1, because if B is given, then that means x of t is greater than A. So we are somewhere, let's see, we are somewhere above this line A. Okay, so that means TA is somewhere to the left of this time point. So it has already passed. So that means if B is given, A is always true. So that is, the probability should be 1. So if we substitute these results into this formula, we have probability of A is equal to, this is 1. So probability of B plus 1/2, and what is it? Probability of A. Okay, so from this we have, let's see, probability of A is twice the probability of B. From this we can relatively easily calculate this probability. So what we are interested in is this probability of A, which is twice the probability of B. But this event B is that x of t is greater than A. Okay? But this x of t follows a normal distribution. So that means, let's write this in the form of 1 minus probability of B complement, actually, less than A. Okay, so this probability is 1 minus this probability, and this is the cumulative distribution function of the normal distribution. So that is this integral from negative infinity to t of this 2 pi sigma squared t and exponential of x squared. Oh, wait a minute. This is not t, but this is A. And 2 sigma squared t dx. Okay. And this is just 1 minus the cumulative distribution function of the normal distribution. of the standard normal distribution with this argument. Okay. But this P of A is probability that TA is less than or equal to some given time point t. So if we look at this result as a function of t, okay, here we have t here, then this gives us the cumulative distribution function of this first passage time. Okay, so that means if we differentiate this function with respect to t, we have the density function of the first passage time. That would be well, we have the cumulative distribution function of the normal distribution here, but here in this case the variable is this t. So if we differentiate it, we should have this result. That is a little involved, but very similar to the normal distribution. T to the power of 3. And exponential of negative a squared to sigma squared t. Okay, again, don't get confused. This is a function of t, density function of t. Okay, so this distribution is called the inverse normal distribution. Okay, so that means the inverse of this follows the normal distribution. Next, we very informally introduce the notion of stochastic differential equations, or SDEs. In the following, we write Wt as the standard Wiener process. So this follows the normal distribution with the standard normal distribution, well, almost standard, with variance t. And if in a similar manner, xt is, if we write xt for a Brownian motion with variance sigma squared t, then we can write xt, okay, if xt is this, then we can write xt as sigma times the standard Wiener process. In this case, it's very easy, but if we deal with this continuous random variable, continuous stochastic process, then sometimes we want to model some random phenomena as in terms of infinitesimal increment of these random variables. So for that, we define some infinitesimal difference of the standard Wiener process, defined by this, informally. So this is Wt plus dt. dt is an infinitesimal increment in time, so we take this difference as dwt. Okay. So this is something like d plus dt, which we have defined before. This is increment, independent increment, stationary increment, independent increment. So if we take this difference in time dt as infinitesimally small, then this is something like a differential. Okay, but as we have seen before, Wiener process is not differentiable anywhere. Okay, so this is not the differential in any ordinary sense. But anyway, so if we adopt this notation, and we could write xt dxt as sigma d wt. So this is an example of a stochastic differential equation. But this is very formally defined. So, this is nothing but a different way of saying this relationship. So it's not very interesting, but this is a start. Okay. In the case where we have a more general stochastic process that is made of a deterministic term and a Wiener process, the standard Wiener process times some constant. Okay, so this part, the second term is a random part, and the first term is a deterministic part because this is just linear in time, and mu is just a constant. So this is a stochastic process that has some deterministic component and some random component. Okay, in this case, the corresponding stochastic differential equation can be written as this: mu dt and sigma dwt. Okay, so this dt is something we usually find in ordinary differential equation. Okay, so ordinary differential equation is something like this. So if we just ignore this random part, it could be the corresponding deterministic version of the ordinary differential equation. It would be like this. Okay, but as we have seen, the Wiener process is not differentiable, so we don't write something like this. Okay, so of course we don't write something like let's see, like this. So this looks more like ordinary differential equation, but we don't do that. Okay, this is undefined because this wt is not differentiable. But actually in physics, in non-equilibrium statistical mechanics, you might find this type of equation where this term is a random force. Okay, so this is an example of the Langevin equation, which is often used for modeling Brownian motion. But mathematically speaking, this is nonsense. Okay, so we don't use it. We write in this way. So far, these stochastic differential equations look so trivial. That's partly because everything is linear. So this is linear in time t, and this is linear in Wiener process. So this is just a linear equation. But what if we have some more complicated form of the function, like there is a function of two variables. Xt is a function of both time and a Wiener process, where this f is a nonlinear function. So if this is the case, then what would be the corresponding stochastic differential equation? To answer this, we need the famous Ito's formula. So Ito's formula. Okay, that is based on, informally, that is based on the Taylor series of two variable function. Okay, let's say let's consider a function f of t and x. Okay, this x is just an ordinary variable, so we can apply ordinary calculus. Okay, so the total differential of this f would be like this. So this is a function of t and x, So first we differentiate with respect to t, and we multiply by dt. And also we have first order derivative with respect to x and dx. And we have higher order terms like 1/2 and second derivative with respect to x and dx squared, and so on. And there are many more terms. But for the present purpose, these three terms are all we need. Okay. So suppose we have this stochastic differential equation to begin with. Okay, and sigma dwt. Okay. By the way, this is called Ito drift diffusion process. So this is the one we have seen before. So it has a drift term here and the Wiener process here. Okay, so formally, let's replace all dx's here and here. Okay, this one and this one. This is dx squared actually with this. Okay, so that would be df would be df dt dt and df dx. Okay, this function f is differentiable with respect to the second argument, so this partial derivative is well defined. Okay, and then we replace dx here by mu dt plus sigma dwt. Okay, so we assume that this infinitesimal differential of x is actually a Ito drift diffusion process here. And also the second order term. Okay, and of course we are assuming that this function f is twice differentiable with respect to x. Okay, and then we replace dx squared by mu dt plus sigma dwt squared. Okay, and then we expand this part. So we have the same term here and plus df dx mu dt and df dx sigma dwt and expanded part. So x squared and mu squared dt squared and 2 mu sigma dt dwt plus sigma squared dwt squared. Okay. Then let's evaluate the order of each term. Okay. So we have dt here, and dw here, and we have d squared here. But this dt squared is very small compared to dt, so we can ignore this term. Okay, and what about those involving dw? Okay, as we have seen, the standard Wiener process, this is approximately of the order of actually not small o but big O, order of square root of dt. Well, roughly speaking. So we treat every dwt as a quantity of this order, okay, square root of dt. So dt times square root of t, so we have something of the order of dt to the power of 3 halves. Okay, so this term can be ignored if we have this dt. Okay, so this is gone. And what about this? So dwt squared will be of the order of dt. Okay, so this term has the same order of magnitude as dt. Okay, so we cannot ignore this last term. So after all, what's left is this. So formally we replace dwt squared as dt. Okay, so just replace this as by dt and factorize. We have this term and this term. Oh, this term. So mu df dx and this term, that is 1/2 sigma squared and second derivative and dt, and the remaining part is this one, so sigma and dwt. Okay, so this would be the stochastic differential equation for this function involving some possibly nonlinear relationship between the stochastic between the random process and the Wiener process and time. And this formula is called Ito's formula. Okay, so usually if we are dealing with ordinary function, not stochastic process, then we could safely ignore this term because this should be of the second order. But in this case, we cannot. Okay. So this is one of the conspicuous properties of the Brownian motion and stochastic calculus. As an application of Ito's formula, let us consider the so-called geometric Brownian motion. Oops. That is defined by this stochastic differential equation. So gt is the geometric Brownian motion, and this is dgt is mu, which mu is a constant, gt and dt, and plus sigma gt and dwt. Of course, wt is the standard Wiener process. Okay, this model is often used for modeling the stock price, for example. So compare this with the stochastic differential equation for the Ito drift diffusion process, which was something like mu dt plus sigma dwt. Okay, the difference is we have this gt, same gt, on the right hand side too. Okay, so that's the main difference. So this makes, for example, if the initial value of gt is positive, then this process always stays positive, because as soon as it becomes 0, it cannot change anymore. So it won't be negative. On the other hand, in this Ito process, this xt can be either positive or negative. Since stock price cannot be negative, it is more reasonable to use this geometric Brownian motion for something that cannot be negative. Okay, so we want to solve this stochastic differential equation, and I cannot tell you how we can systematically solve this equation, but the solution is actually already known, which is this. The solution would be G0 is the initial value and exponential, and mu minus 1 half sigma squared times t plus sigma wt. Okay, so here everything is in exponential function. Okay, as you can see, as long as this G0 is positive, then GT remains positive. Okay, so what we are going to do now is to show that this is indeed a solution of this stochastic differential equation, and for that we need Ito's formula. Okay, so let's do it. First, let us arrange this solution a little bit so that it looks like the original formulation. So G0 exponential, so this part, to sigma squared t, and plus mu t, this part, plus sigma wt. Okay, so this part corresponds to the x in the previous formulation. So let's consider all of these as this function f of x. Then if we differentiate this f with respect to t, we have this exponential function. So negative 2 sigma squared times, since it's exponential, we have this. Okay, and if we differentiate with respect to x here, then that would be, it's just exponential function and with no coefficient in x, so it's just gt. And of course, second derivative with respect to x is again gt. Okay, and then apply Ito's formula. So we have dgt equals to first derivative of f and plus mu, and mu is this mu, this mu, and dx, and plus sigma squared over 2 times second derivative with respect to x and dt, and plus sigma and first derivative of x, that's gt. Let's see, let's write df dx and dwt. So this sigma comes here. Okay, then substitute over the results. We have, this is negative sigma squared over 2 gt and mu gt sigma squared over 2 gt dt and sigma gt dwt, and this will cancel, and in the end we have mu gt dt plus sigma gt dwt as required. So this function is indeed the solution of this stochastic differential equation. Next, let us try to understand the meanings of this stochastic differential equation for the geometric Brownian motion and its solution. Okay, first of all, if we divide both sides by gt, we have this mu dt and plus sigma dwt. So in this form, the right hand side looks just like Ito's drift diffusion process. The only difference is the left hand side. If you use the chain rule, so to speak, although we cannot really differentiate it, this dg over g would be something like log of g differential, right? So if you differentiate this, you should have something like this. So this implies that log dg behaves something like the standard ordinary Ito process. But if you look at the solution, you have this gt g0 times exponential, and we have mu minus sigma squared over 2 times t and sigma wt. Okay, so we have this extra term here. So if you divide both sides by g0 and take logarithm of it, we have log gt over g0 equals to mu sigma squared 2 t plus sigma wt. So in fact, this log of gt with some constant indeed behaves like the ordinary Wiener process with this drift term. But this drift term is kind of dampened by this factor. And this stems from the Wiener process part, because this involves sigma. Okay. This involves sigma, which appears here. Okay. Anyway, this is so log of gt follows a normal distribution with mean this and variance sigma squared. So this means that gt itself follows the log normal distribution. So gt follows a log normal. Distribution. So that means log of g follows a normal distribution. Okay. And if you look up some handbook of statistical distributions, you would find the expectation value of this gt is this g0 times exponential of mu t. And the variance is given by g0 squared exponential of 2 mu t times e sigma squared t minus 1. Okay. So on average, this gt grows exponentially with this rate. At the same time, the variance also grows exponentially with this amount. Okay. in this average value, we don't have any sigma involved, but in the variance we have sigma here. So apparently, the Wiener process doesn't have any effect on the average, but it affects the variance somehow. Okay, now let's look back at the stochastic differential equation. Okay, and that was this. Now, if we ignore the Wiener process part, so if we ignore this part, then we have this equation. So this is actually just an ordinary differential equation, like dgt over dt equals mu gt. And this is very easy to solve, and the solution is gt with some initial condition. We have mu t. So this is actually the same as this expectation value. So on average, gt, this random process, grows exponentially, just in the same manner as the deterministic model. However, since this is deterministic, variance is of course zero, but the difference becomes apparent in variance. Next, have a look again at the solution of the stochastic differential equation here, this one. From this solution, if we ignore this Wiener process part, what we have is this g0 exponential of mu minus this t. Okay, and this is different from this. Obviously, we have an extra term here, which slows down the growth of this. Okay, assuming mu is positive. Okay, so what's the difference? Which one is correct? This one looks more or less okay on average, but if we ignore the Wiener process part from the solution of the SDE, then we are left with some extra term here. So what does it mean? So this means if the variance of the Wiener process is large, then the average growth is average growth is the same, but the variance is different. So as a result, the median will change. Okay, so on average, it still grows exponentially, but if you look at individual realization of this Brownian motion, then it will have a diverse set of possible paths. So many of them will end up not growing at all, or growing very little compared to this exponential growth. Okay, so that's the effect of the noise arising from the Wiener process. And we can extend the Brownian motion in multidimensional space, but in this lecture I will just skip it. But those extension will be important in, for example, in physics, where you need to deal with three-dimensional space. But for today, that's it. Bye.